So today we learning how we can use differentiation to find stationary points and identify what type of stationary points they are. Stationary point is a point where derivative f dash of x equals 0. That means what will be the gradient of the tangent line at that point? 0. That means the tangent line will be horizontal. So we can have three types of stationary point. Minimum, then at this point the tangent will be horizontal. We can have maximum. At this point, a turning point, stationary point, turning point. Again, we have gradient, tangent line horizontal. This is a maximum. And the third type is stationary point of inflection. At this point, and tangent actually cross the line. So this is stationary point of inflection. Stationary, yes, point of inflection. So now we can properly sketch cubic graphs. Before we were able to find only like shape and axis intercepts. Now we can find turning points of the cubic. Let's consider example of function y equal x cubed minus 6x squared plus 9x plus 10. So to find turning points, stationary points, let's differentiate it. So dy over dx will be equal 3x squared minus 12x plus 9. Now we need to equalize it to 0 to find where derivative will be 0. So dy over dx equals 0. We have 3x squared minus 12x plus 9 equals 0. We can divide both sides by 3 to simplify it. We get x squared minus 4x plus 3 equals 0. And let's solve this equation. Let's factorize it. We have x minus 1 times x minus 3 equals 0. So we have x equals 1 or x equals 3. We found x coordinates of stationary points. What should be next? We need to find the y coordinates. Let's sub it in, find y value. So when you substitute 1, we'll get 1 minus 6 plus 9 plus 10, 19, 20 minus 8, y equals 14. Substitute 3, we get x cubed 27 minus 6 times 9 minus 54 plus 27 plus 10, y equals 10. Double checking, 3 cubed 27, 6 times 9 54, 3 times 27 plus 10, yeah, y equals 10. So our stationary points are 1, 14 and 3, 10. So we found coordinates of the stationary points. Does it all make sense what we did?
Yes.
Now we need to identify which type is each stationary point. Now, one thing from knowing behavior of the cubics, you should be able to tell me which one will be which. Because what will be the Because the graph, we have x cubed positive.
114 is the maximum. And
Yeah, so it has to have this shape. So we can say, from knowledge of the cubic graphs, we can tell straight away that this will be maximum and this will be minimum. But let's find it using the proper technique. To do that, we draw number line. And on the number line, we put this x coordinate of this point, 1 and 3. And we know that the gradient is 0 at each of those points. Gradient is 0 at each of those points. So we have that tangent going like this at each point. It's horizontal. Now we need to take one point to the left of 1 and find the sign of the derivative at that point. The easiest will be we take 0. And we substitute the 0 into the expression for the derivative. 9. So it's positive. When derivative is positive, what function doing? Increasing. So we have at 0 gradient positive. It's going up. Then let's take point between these two. We take point 2. Let's calculate value of the derivative. We actually don't need to calculate value. We need to find only sign. We don't need to know exact value. We substitute 2. I will substitute into here to make it easier, because multiplying by 3 will not change anything. So we will have 4 minus 8 plus 3 minus 1 times 3 minus 3. It's negative. So here we have function decreasing. We have here function decreasing. At 3, it's flat, gradient is flat. Now let's take another point, 4. And you substitute in 4 into here, we get 16 minus 16 plus 3 equals 3 times 3, 9, so it's positive. So gradient, we have here derivative f dash of f, or f dash of 0 is greater than 0, function increasing. Here we have f dash of 2 less than 0, function decreasing. Here we have f dash of 4 greater than 0, function increasing. This is called sign diagram. This is called sign diagram. So when we have function increasing, stationary point, decreasing, what we have? Maximum. We confirm that at this point is maximum. Here we have function decreasing, stationary point, then increasing. What we have here? Minimum. That's how we apply stationary points to identify, not just to identify where are stationary points, but we can identify what type of stationary point it is. Yes?
Do we have to do that on a test or so?
Yes.
The number line bit?
Yes.
Okay.
Yes. That is how you find what is at that point. Now, we got maximum minimum. Let's consider a case how it will look if we have stationary point of inflection. Let's consider another function, y equal 2x cubed minus 5. Let's consider function y equal 2x cubed minus 5. Derive
6x squared.
equal 6x squared. 6x squared equals 0. We have x equals 0. So we found that there is a stationary, only one stationary point at x equals 0. Now we again draw number line Again, knowing the cubic, we can already say what is there. But let's do it properly. By the way, let's find y coordinate. What will be y when x equals 0?
Negative 5.
-5. So stationary point is at 0, -5. Now we put on the number line, we put only one number, 0. We have only one stationary point. Now let's take one point to the left, easiest -1. We substitute -1 into expression for derivative, and we get f dash of -1 is 6. It's greater than 0. We take 1, we get again f dash of 1 greater than 0. So we have function increasing, then stationary point, and increasing again. That is stationary point of inflection. Does it make sense? So from now on, when you need to sketch cubic graph, you will need not just label x-intercept, you will need to find the stationary points and label them, because now you have tools to do that. Before you could not, now you can. So you will have to do it. And one more application is absolute maximum and minimum. Absolute maximum and minimum. That type coming up if we have function, not like in previous cases we did not have any limitations on the domain, but if we have limitations on the domain. For example, let's consider function. Let's consider function y equal y equal 2 minus 8x squared with a domain from -2. So I will write proper notation to remind you. So let f double dot minus 2 to r and f of x equal f of x equal this. Using proper function notation, reminding you f domain, actual domain, to r, it's always r, doesn't matter if it's not all real numbers, you still need notation right now. And then you comma and you write function. And we need to find the absolute maximum and minimum on this interval. First, let's derive it. Let's find f dash of x, which will be pretty simple in this case, equal -16x. Equalize it to 0, -16x equals 0, x equals 0, and y equals 2. So we have stationary point at 0, 2. What type of stationary point?
Oh, no, never mind.
What type of stationary point it will be? Without doing any sign diagram, thinking about the graph, would that?
Maximum.
It will be maximum because it's upside down parabola. So we have maximum. But now we need to compare this value with the values at the end points to find what the absolute, what will be on this interval will be the biggest y value and what will be the smallest y value on that interval. So f of -2 equal 2 minus 8 times 4, so equal -30. F of 2 equal will be exactly the same thing, equals 2 minus 8 times 4 equal -30. So what is the smallest value of y on the given interval? Negative 30. So absolute minimum equal negative 30. Absolute maximum equal at the turning equal to. Sometimes in the questions you might get that this is a maximum. For example, if we have, let's say, cubic, but we consider that cubic only on this interval. Only, no. We consider cubic, we have limited domain and we consider it on this interval. Those are endpoints. Where will be absolute minimum?
The left.
Left endpoints will be absolute minimum because it has value less than the local. Those called local maximum, local minimum. This is absolute minimum. And this will be absolute maximum. Questions? No? Like, subscribe, and donate to help fight terrorist countries and organizations, Russia, Iran, Hamas, etc. Support Ukraine and Israel.